time for some review. And we're going to be reviewing two topics, Laplace transforms and series. We'll start with Laplace transforms. And to start, let's talk a little bit about what Laplace transforms are, why we do Laplace transforms, how we do Laplace transforms. So we'll start with the what. So essentially what we have is we have a space of functions, and these are functions which are in a variable called t. And then over here we have another space of functions, and these are functions of the variable we call s. And so what are we going to do? Well, Laplace transforms is a way to go back and forth. And so in particular, the Laplace transforms, that goes, you start with a function in t, you end with a function in s. The inverse Laplace transform goes the other direction. Namely, you start with a function in s, you end with a function in t. Now, not every function in t comes over, not every function in s actually belongs here, so nor can it go back. But for the type of functions that we have frequently encountered this class, we will be able to go back and forth. So, okay, all right, so that's the what. It's essentially saying we go from a function in one part to a function in another part. And now you're just like, why? Why would we do this? Well, okay, here's the idea. Oftentimes when we are solving problems, we're solving problems about functions. When we think about differential equations, the goal of differential equations is to find a particular function which satisfies a property. So what we can do is we can say, well, there's a problem that's over here. It's a function in t. Solving a differential equation, it can be other things as well. And this problem is hard. But when we come across to the other side, all of a sudden, this becomes less hard. Now, I don't want to write easy, because I don't want to trivialize things. It's a different type of problem. And in particular, what often happens is that when we start with a differential equation problem in t, when we move it across to s, we're ending with an algebra problem. So we're transforming one type of problem to another type of problem. And so we can say, we're a little bit better at algebra than we are at differential equations. We're definitely a little more practiced. We've been doing it for a long time. So that's why it's a less hard problem for us to solve. So we can do the solution part over where we're more comfortable, and then we can pull back the answer. Okay, so that's a little bit of the why do we do it. Now, how do we do it? Well, there's sort of two answers. The first answer is there's a rule. It's not one of the rules that you see here, but we'll get to that in a minute. The second answer, and this is the more realistic answer, the one that's more practical. So how do we do Laplace transforms? And the answer is table. So what we have is a collection of rules. And the rules are going to help us carry out the Laplace transforms that we care about. Now, obviously, the table is not complete. There are many more functions that one could always add, but the table is complete in so far as we are concerned. So it has the functions we'll care about. Now, what do I mean by table? Well, I mean that we'll have a collection of rules, and they sort of fall into two main categories. There's rules about what happens to particular functions, and there's rules for about how do we combine things together. And so what we'll do is we'll say, if we want to do a Laplace transform, we rewrite our expression so that it fits our table, and we have lots of nice things to use. Linear says that we can break things apart, we can move constants in and out, we can use identities, we can do all sorts of things. And so we rewrite until we can apply our table to each piece we come across. To go back, same idea. Say, okay, rewrite. So we can apply our table to each piece and work your way back. So it's about a table. Now, if you're uncomfortable with that idea, just realize you've been doing it. How do you do derivatives? How do you do integrals? You have a table. That's how you do it. And you say, okay, but I just know it. Yes, you know the table. And one day, if you keep working, you'll know the table for Laplace transforms, just like you know the table for integrals and derivatives. And so for now, the good news is we'll give you what you need. All right, so let's start talking about our table. So we have our first part we're going to talk about is the functions. And so there's a variety of functions, but you'll notice they fall into some very familiar categories. There's exponential, and that's a very important function because we love the exponential function. So the Laplace transform of e to the ct, 1 over s minus c. So you notice how we start with the function t and with the function in s. We have powers of t. Now t to a whole number, positive whole number, that's not too crazy. N factorial over s to the n plus 1. We can even do t to fractional numbers if we use this gamma function. Now gamma is a function that behaves a lot like behaves a lot like factorial, and but it fills in the in-betweens. Whereas factorials, you have to do whole numbers. Gamma says, no, I gotcha. I'll do any positive number. And what do? Well, there's a complicated integral, and it's hard to compute explicitly for many cases. So other than whole numbers, which we already can handle, the only other case we'll focus on are halves. Now, gamma of a half is root pi. Well, how do you get gamma 3 halves? Well, you use a relationship. So gamma 3 halves, well, that's gamma of a half plus 1. So that would be a half, gamma half. And so that would be a half root pi, and so forth and so on. And all right, well, that's the idea. Oh, I forgot to mention sines and cosines, of course. I should have mentioned sines and cosines. And no surprise, they are fairly similar. Cosine, s over s squared plus b squared. Sine, b over s squared plus b squared. We can even add factors of t as well. And we'll talk about how we do that in general. So, all right, so we have our functions. Notice we've written this in terms of Laplace. We can have also have written in terms of inverse Laplace. So, for example, the inverse Laplace of s over s squared plus b squared is cosine bt. So there's really a pair of rules. So for each rule for Laplace, there's a rule for inverse Laplace. So, all right, there we go. Now let's keep looking at more rules. So not just functions, but rules for things to do to functions or ways to combine. Now the first thing we see listed here is the definition. So this integral is how we actually do a Laplace transform. And in practice, we will never do this integral. We only use it when we encounter something that says, okay, how do we do this? Well, if we don't know yet, we apply the rule. But of course, we know our basics. Now you might say, do we ever use this definition? Well, yeah, one of the things is oftentimes we think about taking function to function. But when we have a function in s, we can always evaluate it at a point. And so evaluating s at, say, s equals 2 is the same as computing this integral e to the minus 2t. And now we're like, oh, so that gives you a way to carry out a crazy integral that would otherwise be a little bit difficult to find out. Now, what are some other things? Well, if we multiply by an exponential, that results in a shift in the answer. And it's not too surprising because we see that there's an exponential function in the definition. There's a strange kind of multiplication called convolution. So this is convolution, and it takes two functions and produces a new function. And it does this by creating this integral from 0 to t, f tau g of t minus tau. So in some sense, f is going this way and g is going that way, and you're somehow combining them together. Now, it's not the most obvious way to do multiplication, but the really beautiful thing is when you do this, f star g, the Laplace transform, is the Laplace transform of the individual pieces. So in other words, it's really easy to carry out the Laplace transform of an integral that's set up in this way, which is really fun. We also have a rule about what happens if you multiply a function by t. Well, in that case, you take the derivative and add a minus sign. So it says, okay, so there's ways to put in factors of t. And, all right, what if we find the antiderivative? Well, to find the antiderivative, we divide by s. And, of course, there's a few more. Again, we'll talk about some as we go on. We have, of course, this mindset that, as we've said, every rule for Laplace comes with a rule for inverse Laplace. And so, all right, well, what's some examples? Well, let's take this one. If you take the inverse Laplace of both sides, what do you get? Well, this becomes t f of t is equal to minus, and then you can say inverse Laplace of f prime of s. But now what we do is we say, well, f of t, that's really, if we think about that, that's the inverse Laplace of f of s. And so we can solve, and we get the following. We can say, all right, so f of t, which is the inverse Laplace of f of s, is minus 1 over t, inverse Laplace of f prime of s. So this rule here translates into another rule for inverse Laplace. It says, look, if you're trying to find the inverse Laplace of a function, you can do it for its derivative. So in other words, if you have something that's really bizarre, how do you do that? Well, was the derivative nice? Yeah, the derivative's nice. Then use the derivative. And don't forget to add a factor of minus 1 over t. And so similar things happen as well. For instance, if you talk about this rule, what does this say? Well, it says the inverse Laplace of f of s minus c. So if we ever see a shift going on, so all the terms have s minus something. So every s looks like s minus something. Well, according to our rule, this would be e to the ct inverse Laplace of f of t. Sorry, excuse me, f of s. So it would be e to the ct f of t, so f of t is the inverse Laplace of f of s. So okay, so essentially says, if you see a shift, add an e to the ct, and figure out what to do without the shift. All right, great. And, well, okay, one more. And namely, well, let's do this one here. What does that translate into? Well, it says inverse Laplace of two things multiplying together. If we don't know how to do that, well, what we can do is we can say, all right, well, that's really the inverse Laplace of the first thing, the inverse Laplace of the second thing, and then do the convolution. And so those are our rules. Now, there's a note. Many problems are like onions. They have layers. So you have to work through the layers. And of course, you might say, I know what you're going to say. There also are going to be tears involved, right? Tears of joy. Tears of joy at doing fun and interesting problems. So if you do see something that looks complicated, don't panic. Start saying, okay, can I rewrite it? Or can I just sort of do a piece of it and then do a bigger piece? And just think about how things combine. And once you understand how rules work, life becomes easier and problems become fun. And then we get to enjoy everything. We've already mentioned how Laplace transforms takes a hard problem and turns into a less hard problem, right? And the hard problem we're interested in, of course, is solving differential equations. And we've talked about various techniques, but for right now, we're just saying, okay, how can we use Laplace transforms? And they actually are fairly useful, Laplace transforms, for solving particular types of differential equations. Namely, any time when you have a piecewise function involved, or pulses, which we'll talk about in a few minutes. So how does one go about it? Well, there's a nice fact which says if you take, say, the derivative and take the Laplace of that, then that's s x of s, where this is the Laplace transform with no derivative attached. So in other words, taking derivative essentially adds a multiplication by s. And then there's a little piece you have to pay attention to. Taking two derivatives, it adds an s squared. And again, some pieces you have to pay attention to. But the punchline is that taking Laplace transforms of derivatives, not so bad. You just have s to a power times what you're looking for. So how do you do this? How do you use Laplace transforms to solve an ODE? Well, there's 3 steps. What's the first step? You start with the differential equation and you say, what is that going to become? So our differential equation starts in t. What does it become in s? So you take the Laplace transform of everything, both sides, and you say, okay, how do you do that? Well, the answer, table. That's right. We look at our table, piece by piece, we say, all right, what's going on? How do we do our Laplace transform? Okay, so we've transformed our setting. Started in t, now we're in s. In s, we say, let's pull out our algebra skills. And so in particular, we're going to solve for capital X. That's our function, really. And we say, okay, that's not too bad, solving for x, getting x by itself. The next part is the tricky part. We want to rewrite it in a way that's going to be friendly to our inverse Laplace transform, right? And so there's a bit of work to be done. So this is algebra. Now, what kind of algebra does that involve? Well, it's things like adding things together, possibly doing partial fractions, and understanding the setup. All right, what's the last thing? Once we're ready to take the inverse Laplace, we do. And why do we do it? Well, because if we take the inverse Laplace of capital X, we get little x, which is what we're after. And so that's our answer. Now, of course, we have to do the inverse Laplace of what's on the other side. And how do we do that? We use our table. And so, don't try to be a hero. Don't be like, I'm never going to look at the table. No, look at the table. It's your friend. And use it. Make sure you can get the 2 sides. Because when I say the 2 sides, the basic idea is you can imagine that there's this square here. And we wanted to go from problem to solution. And the way we do it is move to a different problem, solve that other problem, and then say, aha, how does that problem give us the original? So the 2 pieces here, those are using the table. And the last piece here is algebra. And so the table is super important. Know it, use it, learn it, live it. All right, good. There's one more thing we should talk about with Laplace transforms, and that's U and delta. Now, delta is for a pulse. What is that? Well, that's if you have, say, a system, could be a spring, for example, and you whack it with a hammer. So it only happens in one instantaneous moment. So anytime something happens and you say, it just happens, it's a one-time event, instantaneous, and nothing happens before or after, just at that moment. Okay, that's a delta function. The other thing is U. U is an on-off switch. And so U, what does it actually look like? Well, U of t minus a, it's what's called the unit step function, and it does the following, namely, it hums along at 0 until you hit A, and it says, now I'm going to hum along at 1. And so it's turning something on at time 1. And so, all right, what do we have? Well, delta t minus a, e to the minus as. But the important one, u of t minus a, f of t minus a, is e to the minus as. So notice there's some similarities going on here. F of s. All right, now be careful here. There are some things that you have to pay attention to. So when you see this, you'll see, okay, if you ever see a u of t minus a, you know that goes with e to the minus as. And in a similar way, remember, we have our pairing up. There's rules for Laplace, or rules for inverse Laplace. And so when you see the inverse Laplace of e to the minus as, well, this tells you that it pairs up with u of t minus a. All right, so that's u of t minus a. And, all right, but the other thing to keep in mind is the piece that's attached. And this is where things get a little bit subtle. Namely, notice here this f of t minus a. It's not f of t. It's f of t minus a. In other words, it's been shifted over. So it's not enough for us to say, oh, it's just f of t, life is good. You have to make sure that whatever is attached is in terms of t minus a. And so there's some good advice here. If it says, if you want to rewrite a function in terms of t minus a, which you do, if you're going to apply this, well, anywhere where you see t, you can write t minus a plus a, and then work with the expression and clean it up. So, okay, all right, good. Now, so that just means be careful. So, if I see a u of t minus a, oftentimes what I'll do is I'll say, all right, first think about what does f of t mean? You know, in other words, what's the f of t attached to it? And that's what's going to give me f of s. Similar, here I say, okay, well, f of s, that gets me an f of t, and then we'll do f of t minus a. So make sure you have that intermediate thing going on as well. Now, why do we like u of t minus a? We talked about delta. That models your boom, your pulse. What does u of t minus a do? Well, u of t minus a is piecewise. Anytime you have a function which changes behavior, so anything causing it to change behavior, it could be a picture where, you know, there's several parts, each one is different. Could be a function that says, okay, from 0 to 5 you do this, from 5 to 7 you do that, 7 to infinity you do that. It could even be other things that are more subtle, like, well, it's the square root of, or sorry, not square, absolute value of t squared minus 5 or something. So anything where your function changes behavior, you say, okay, that's piecewise, and if I want to feed it through the Laplace transform machinery, I have to rewrite it in a way that's compatible. And the way that we can do that is using our on-off switch. So what we do is we break it up into several pieces, and each piece represents a change. So you say, okay, we have the initial, and then we go along and say, okay, suppose there is a change at time a. So what we need to do is we need to turn off what happened before time a. So we subtract that. We need to turn on what's going to happen after time a, and so we add it. So it's u of t minus a, behavior after time a, subtract behavior before time a. And we do that for every time that there's a change. And that gives us a way to really put our, as I said, our piecewise function into a nice form that we can now use our machinery on. So there we go. That's the ideas. Now we're ready for Laplace transforms. It's, from here, practice, of course, but it's the ideas. We have our tables, make things look like what's on our tables, know how to use our table, and be ready for algebra, including partial fractions. Yes, they will show up. Now we're ready for our second topic. Our second topic is about series. It brings us back to our wonderful happy days of Calculus 2, when we first started talking about these things. And at first we said, oh, what an interesting idea. Let's dip our toes. And then our teachers were like, no, 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 we're going for it. And we're just jumping in like a polar bear plunge. What a shock to the system. And, hopefully we've now recovered and we're like, okay, I kind of get what's going on. Well, I hope we at least have reached that point. So what's going on? Well, series means that we're going to think about our solutions as these really big polynomials. So a series is nothing more than essentially you can think of it as an infinite polynomial. ck x to the k. Now, why do we care? Well, the nice thing is that most good functions, such as, for example, our solutions to a differential equation, can be written at least nearby as a series. So in other words, we could say, this looks like what our solution should be. And what do we need? Well, we need the constants, the c sub k. So how do we go about finding them? Well, there's some good news. There's a couple things we can do. So we have some initial conditions, and depending upon how many initial conditions we have, those will give us our terms at the start. So if we have, say, one initial condition, because it's a first order differential equation, gives us C0. If we have two initial conditions, say it's a second order differential equation, it'll give us C0 and C1, and so forth. But usually for right now, since we're beginners, we'll stop at second order. So it gives us the start terms. And you say, okay, well that's nice, but how do we get more? We want more, we want more. Well, we're going to use a really cool fact, which says, since we have polynomials, what we're going to do is we're going to make everything in our differential equation look like polynomials. In other words, we're going to make them look like series as needed. And then we're going to push everything together. And our idea says, okay, because I have an equals, I have a polynomial on the right, polynomial on the left. And these polynomials are equal if and only if the corresponding coefficients of x to the power are equal for all powers. So what we're going to do is we're really going to push so that everything with powers of x to, let's say, L, all the powers of x to the L are together. And so we can really read off coefficients. And now the beautiful thing is every term gives us a new constant, one of these new c's. So the constant terms will give us our next c. The terms in front of x gives us our next one. The terms in front of x squared, our next one, and so forth and so on. All right, now, there's two ways that we're going to talk about doing series. The first one is recurrence relationships. Now, recurrence relationships say we're going to keep our sums all the way through. And what we're going to do is say, all right, we're going to take our expressions, so we're going to put in y for everywhere we see y, including y prime. Now, how do we take derivatives? Term by term. How about second derivatives? Well, just do derivatives twice, term by term. And then you say, okay, I replace the y prime, the y double prime. I might have to do a little bit of multiplication. I move any powers of x in the front into the sum. And the goal is to write it as one giant sum. As we would say, one sum to rule them all, right? A single sum, so we have all the powers of x to the L together. How do we get there? There's 3 steps. The first thing we want to do is we want to make sure all the powers of x look the same in each individual sum. So we have several sums we have to put together. So we do this by shifting. So we say, okay, if I see x to a power, I'm going to shift. So if it becomes like, say it was k minus 3, I'm going to say, okay, I'm going to let L be k minus 3. So, all right. So now it looks like x is L. So when you do that, you have to replace all the k's. And you do this for each individual sum. Now, each sum may have a different shift. That's okay. Now that you've shifted and say, okay, that's going to make all the powers easy to put together, you say, all right, now look at the starts. You want all the starts to agree. So in other words, you all want them to start at, say, 0, or you all want them to start at 2, or 3, or 1. Whatever the number is, they have to agree. What if they don't agree? Well, we're going to peel off terms from the starts as needed so that what's left all agrees. Okay, now the last thing is we combine. Yes, we combine the parts that we peeled off, and then everything else we put into our big giant sum. And with that big giant sum, we look at the coefficient of x to the L, and that is the recurrence relationship. What is the recurrence relationship? It says, if I want to find something, I look at the things that came before and I apply some rule. That's all it says. So I can find what I'm looking for in terms of what came before. And so it's a rule for finding more coefficients. All right, and once you have that, you can now just start churning them out one at a time. And you start, okay, what's the constant? What's the coefficient of x? What's the coefficient of x squared? Da, 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 da. And life keeps going. Now, the second thing we'll do is say, well, what if we don't actually have to find the recurrence relationship? Maybe we're just after an approximation, which is not unreasonable. In life, we often say, look, we can't find it exactly, but an approximation is good enough. That's one of the things that's happening with series. It says, look, sure, if I go all the way to infinity, I got it exactly. But if I go all the way to 4, I've got it pretty good, at least nearby. And that might be enough for me to understand what I need to understand. So we say, look, if we're only after a few terms, what do? Well, we're going to put in just enough to give us what we need. Now you might say, well, wait, what do you mean by just enough? Because that's a little vague. Well, okay, so let's talk about just enough. Again, our goal is to compare coefficients. And so we want to have enough coefficients to get what we want. Now, initial conditions give us our start terms. So we say, okay, so what we do is we say, how many terms are we looking for? And that's some number. So maybe we want, the first 5 terms. C0, C1, C2, C3, C4. Then we subtract the number of initial conditions. And the reason we're doing that is the initial conditions, they're giving us solutions. So this is how many terms left to find. So let's suppose we want 5 terms. Initial conditions gave us 2. That leaves us with 3. So how much do we look for? We need to have the constant, the x, and the x squared. So we go through and we replace everything with enough of the series so that we get the constant, the x squared. And now we say, okay, what's going on with those 3 terms? And everything else we don't care about, so we put it as plus dot dot dot. Just another way of saying, and there's more stuff, but we don't need it. Or we could say, aha, there's more stuff, and the pattern continues. But for now, those are our 2 ideas. So if we're after recurrence relationships, keep everything as a sum, make one big sum. If we're after just a few terms, put in just what you need and do the comparisons. At the end of the day, it's the same idea in play for both. We gain information by comparing coefficients. It's just a matter of how far do you want to go. And so that's our idea. We're avoiding all the messy stuff about things such as, okay, what's, does it mean to converge, radius of convergence, things like that. We're just avoiding that for right now. Wonderful discussions that could be had, but for right now, we're just getting into the practice of using series and getting the hang of it. All right, well, that was our quick review of Laplace transforms and series. Life is good. We're going to be great. We know what's going on. So let's go and do wonderful. Bye.